Hello there. This video is on section 11.7 on how to develop a strategy of which convergence test to use with a given function. This is one of the things that calculus students often struggle with when they're learning convergence tests, is when you get a random test or a random series, which test should you use? So I'm going to give some tips and ideas here on just that, how to decide what test or tests are good to use for a given series function. Okay, so starting off, just some reminders. Um, we have learned about 8 series tests. I've listed them right here: divergence test, geometric series test, etc. I don't need to read them out to you. Those are the ones we're going to be choosing amongst. I have put onto Canvas a summary of all of those convergence and divergence tests. So you can see all of them right here. And this might be handy to have available when you're doing series tests. Back to the notes. There's one more thing that I'm going to give as an idea that helps quite a bit of people, is this idea here about the hierarchy of functions. So there are functions that go off to infinity. You've learned all the basic functions in your pre-calculus class: logarithms, polynomials, exponentials. We've added in this class factorial functions, power x to an x, like variable to a variable type functions. Um, and those are the types of functions that go to infinity, but it turns out that they are not treated the same. We use this double less than sign to say that it's like significantly less, like amazingly less than, I don't know what the extreme word is. So ln x is really, really less than a polynomial function, x to the p, for any value of p is greater than 0. I'm going to give you just a kind of fun visual idea of how this works by choosing a natural log function and graphing it, and then an exponential, then a power series here, like a polynomial type function, then an exponential, and then a factorial, and then this x type function, and show you visually what I mean by like really, really different sizes. So all these functions are going to go to infinity. Let me just show you on Desmos. So my first function here is ln x, and ln x has this classic shape where it dips down to negative infinity where x is 0, and it goes up. It doesn't go to infinity fast, but it definitely goes to infinity. And for a matter of scale, I've seen what the ln of 10 is. It's about 2.3, so I made my y-axis high enough that I could see that value. All right, so now I can do the same thing with like a regular polynomial, like just x squared. So again, I'm starting at 0 and I'm going off, and you can see it's much steeper. To get an appropriate scale, I'm going to see what it is at 10. At 10, 10 squared is 100. So going up to 6 or 7 isn't really going to show much of this graph. I need to go up to 100. So I use a little wrench here, and I'll make the y value 100. And now you can see this x squared graph, and it doesn't go off the screen as much. Here at 10, you can see it goes up to 100. Let me add back in the natural log graph. And you can see, remember, the natural log graph goes to infinity, but it does so much slower than this just basic x squared graph, right? So the x squared graph kind of just goes off almost like the log graph isn't doing much at all. That's how much bigger just a regular polynomial like x squared is compared to a log graph. All right, we'll do the same thing with an exponential. So here's e to the x. Classic e to the x goes flat and then goes up like this. I do need to change the y-axis because it goes off the top of the screen. I just put in e to the 10. I put in the x value of 10. That's about 22,000 and some change. So I'll change my scale here to 22,000 and some change. I'll just make it 23,000. Doesn't really matter that much. So there's that thing right there. You can see now when x is 10, we can kind of see where the function is. It's right up here. Let me move me over here somewhere. Okay, so let's bring back in our log graph and our x squared graph, and they're way, way down there. You can kind of see them basically right where the x-axis is, they're not growing at all, right? I mean they are, obviously they go to infinity, but in comparison to this new exponential graph, they are almost flat. That's how much faster, how much larger the exponential graph is compared to a polynomial versus a log graph. Okay, let me add in the next couple ones. Here's a factorial function, y equals x factorial. I do need to go up again with the y scale. This is about 3.6 million. So I will change my scale to be able to see the top of that. I'll just do 3.7 million. Okay, so doing that, then you can see the top of this x factorial graph. And I don't know if you can see, but here's like the green graph here. If you're excited to see the green, that one there is the exponential e to the x. The blue one is under there. That's the x squared one, and the red one, which is the ln x, I can't even see anymore. It's like so close to the x-axis, it's almost vanished. And we'll put the last one in, x to the x. I need to change my y scale to 10 to the 10. I'll do so real quickly. So we'll do, whoops, get rid of that stuff. 1 times 10 to the 10 is my y-axis. And now we can see this new graph in black. That's x to the x. I'll scroll out just a little bit. You can see this purple graph, but it's overshadowed by the black graph as I go further and further up. And then the other graphs, like the green graph, and if you zoom in, maybe we'll see the blue graph and maybe the red graph. I mean, they're just so minuscule. I could zoom in almost, for a long, long time before I'll ever get a chance to see these smaller functions. So this is called the hierarchy of functions. Each function is substantially larger than the previous one. So why does that help us? Well, when we're doing a series test, it really kind of helps to think about what kind of terms dominate other things. If I were to mix a couple of things together, if I was to mix an exponential along with a polynomial, the exponential is so much bigger that the polynomial almost doesn't matter anymore. So you can kind of focus on the exponential and use that as a guide to think about, okay, does this converge or diverge? What kind of test can I use for exponentials? Those sorts of things. So the hierarchy of functions is what advanced math students do when they're looking at a function, and in this particular situation, a series that has a function in there. All right, let's do some example problems so you can kind of see this in action. By the way, the series tests, I'll just give a couple comments. The divergence test is always a good one to consider trying first. It's just a simple limit, and it's usually is very quick to do a limit. So if you want to be quick at it, divergence test is always a good place to start. If you have an exponential function, that's a geometric series test. If you have a polynomial type function, like x to the p, that's a p-series test. Integral test is for functions that looks like you could anti-differentiate them. Limit comparison test is when you can simplify part of the function, like you can throw part of it away or simplify it dramatically, then the limit comparison test works. The direct comparison test is like the limit comparison test, but you use it when the limit comparison test doesn't work. I'll show you an example of why it might not work. The ratio test is a great one when you have factorials or combinations of functions, but you don't have n to the n. You don't have that, x to the x variable to the variable type formula. And the root test is when you do have that, n to the n type formula. Okay, so let's look at this example A. I'm given this series right here, n squared over e to the n. As I mentioned before, it's always a good thing just to give the divergence test a try. The divergence test is you take the limit of the sequence, not the series. So I'm going to take the limit, oops, I mean x's, and goes to infinity of the sequence, n squared over e to the n. And if you have your series test sheet handy, or if you remember, if this limit does not equal 0, we immediately know that the series diverges. This is infinity over infinity, so we can use L'Hopital's rule. And then we differentiate the top. Whoops, I got to write my limit in there. differentiate the top, differentiate the bottom. It's still infinity over infinity. So I can use L'Hopital's rule again. And I get now 2 on the top and still e to the n on the bottom. So this becomes 2 over infinity, which is 0. So unfortunately, we didn't get a non-zero result. If you get a non-zero result, you immediately know the series diverges. We got 0, which doesn't really tell us much, doesn't guarantee this thing converges, but we didn't learn much by doing the divergence test. Let's examine this series a little bit more deeply before doing any other tests. We have an n squared on the top. An n squared is an x to the p type function, right? Variable to a number, n squared. N squared is a variable to a number. X to the p is a variable to a number. And the e to the n, the e to the n thing is a number raised to a variable. That's called an exponential function. That's this guy right here. Notice that the exponential function is way bigger than the n squared type function. So we basically can almost ignore the n squared function because the e to the n is so much bigger. You have this gigantic big thing on the bottom. You have something insignificant on the top. When you have a really big thing on the bottom and something not really that important on the top, we're going to think that this thing probably converges, right? Because if you have things that are going to 0 very, very quickly, you're going to be able to show that it adds up to a finite number. All right, so whether or not that's useful, we're kind of expecting this to converge. This will help us if we use the direct comparison test, and also if we do other things where we need to have an idea of which direction to go in, whether it converges or diverges. All right, so what can we do here? Well, given the fact that it's kind of like e to the n, let's try the comparison test. Specifically, the limit comparison test is what we're going to try first, just because it's easier. So for the limit comparison test, what you do is you come up with a new function, a simplified function. So you have a simplified, we call it like a bn. And remember, we said that n squared over e to the n, the n squared really just wasn't doing anything compared to the n. We're just going to throw it away. So for a simplified function, you can do whatever you want. I'm going to throw away the n squared, and I have something like this. So once you have a simplified version of your series, then you do the limit as n goes to infinity. Again, you're looking at a sequence. But in this time, we do the ratio of an over bn. So we do this right here. So here we have to get a non-zero answer for us to make a conclusion. So let's see what we get. So an is our original series or sequence. Bn is our new one. I'm going to do my algebra simplification here. And we do have some division, which is quite nice. That's supposed to be infinity. We get the limit as n goes to infinity. And we just have n squared over 1. So this is just n squared. And that's infinity squared. And so that is infinity, right? It's definitely not 0, right? So it's definitely not 0. So what does the limit comparison test says? Well, you take the limit of a ratio of these two sequences, and if you don't get 0, then either they both converge or they both diverge, right? So we know that an and bn either they do the same thing, right? So we know. So both an, which is our, I'll just write the original series in there. An is our original series, and bn was our simplified version. Both either converge or diverge. So that's the limit comparison test. However, we know this guy. This guy converges by the geometric series test. It's a geometric series test because it has an R value of 1 over E, right? So if you have a, exponential type function, the base of that thing, which in this case is 1 over E, that's the thing that determines whether it converges. If that ratio is less than 1, then we know that the thing converges. It's actually the absolute value is less than 1, but in this case, it's definitely less than 1. So I'll just put the absolute value bar here so people will remember that it could be like negative as well as positive, and it still will converge by the geometric series test. So because this thing converges, thus the other one, the more complicated one, also converges. Converges, I spelled that wrong, by limit comparison. Okay, so let me zoom out a little bit here. So our strategy for this particular problem, well, first we tried the divergence test. So this one right here, in case I said it, but in case you missed what I said, this is the divergence test up here. So first we started a divergence test because it literally just takes 30 seconds to see if it diverges, and it would if the limit was equal to 0. It doesn't, so we don't know anything. We started analyzing the function, thinking that this is kind of like e to the n type function where the n squared doesn't really matter. So we're going to just use a limit comparison test with a simplified version. And we got a simplified version being 1 over e to the n. And then we did the math, and the limit ended up being a non-zero. When limit's non-zero, we know that either they both converge or both diverge. But our simplified version, because it's simplified, was very easy to notice that it converges by the geometric series test. And let me spell this better. And therefore, we know that the other series converge as well. The original n squared over e to the n series converges as well. That's by the limit comparison test. All right, a couple of other side notes just to try to help people understand this better. We have solved the problem. We don't need to do more. But one thing students will ask about oftentimes when they're learning this is that, well, how do I know what simplified formula to use? And we use a simplified version of this. When we looked at this guy, we just kind of threw away the n squared. And we said, okay, well, let's try that. Well, how do you know which part to throw away? And the hierarchy of functions is going to kind of guide you as to what dominates. The e to the n, the exponential function completely dominates the n squared, the polynomial function. So we really need to focus on that. But suppose if you chose the bn equal to, let's get rid of the e to the n, right? So remember our an is n squared over e to the n. What if we chose our simplified version to get rid of the e to the n and just be n squared, right? So this is not going to work, but I just wanted to show you why it doesn't work. So suppose you simplified it the quote unquote wrong way, right? And you got rid of the e to the n and you just get n squared, right? So then what happens, right? So then you do the limit as n goes to infinity of the an over bn, which is n squared over e to the n over the n squared. So we're still doing the same limit comparison test, but with our new version of bn. We got to do our simplification here. That would be n squared over e to the n. And then I need to simplify the over n squared to be times 1 over n squared. We do get that nice simplification again because you have a division of the same thing top and bottom. And then this becomes the limit as n goes to infinity. All that's left is 1 over e to the n, which goes to 1 over infinity, which is 0. Remember, the limit comparison test needs to have the limit of the ratio, the an over bn, be non-zero for it to tell us anything. So if you chose a simplified version which didn't work, you're going to find out very quickly that you threw away the wrong part because you do get a limit of 0. and it doesn't conclude anything, we need the limit to be non-zero. The other quick ditty I will add to this sort of discussion is that this original series, I'll zoom in a little bit, you can also do by the integral test. We can integrate this thing. It requires integration by parts 2 times. One part reduces the n squared to the n. The next integration by parts reduces the n down to just a constant. So you could integrate this. So this is integrable, which means you can use, or antidifferentiable, so you can use the integral test to determine the convergence and divergence of this series as well. I say this because on a lot of these series, you have options. It's not like you have to find the one right way. The direct comparison test works here, the limit comparison test works here, and the integral test works here. The 3 tests that are go-to for this type of problem. When you do, dozens of these types of problems, you'll start to spot the, candidates that are useful. But in fact, that's the reason why we're doing these examples in the video today, is just to help you build up some experience on, things to use for different types of series functions. All right, let's look at some more examples. All right, so my example B over here. There we go. We have n factorial over n squared times 2 to the n. Once again, we can just say, hey, let's look at our divergence test. So you take the limit and then goes to infinity. You get n factorial over n squared times 2 to the n, which, by the way, does go to infinity over infinity. The question is, I don't know how to differentiate n factorial. N factorial is like n times n minus 1 times n minus 2. There are so many products of n's and n minus 1s and n minus 2s and n minus 3s. I don't even know how I would go about doing this, right? So even though L'Hopital's rule is a great, strong, theorem or rule, I don't think we can use it here because we don't know how to use it on n factorial. So cheap divergence test didn't work, not because it got 0, but because we don't really know how to find the limit very easily. We could do other methods, but let's just kind of go down a different path because the divergence test is supposed to be quick and easy, and it's no longer going to be either of those things. All right, so going back to sort of the tips I gave on the previous page, we have n factorial, we have n squared, we have 2 to n. We have a factorial type thing, we have a polynomial type thing, and we have an exponential type thing. So what do we do here? Well, it says down here, when you have factorials or combinations of functions, but no n to the n, that's a great time to consider using the ratio test. And in fact, that's what we have. We have a factorial, we have a combination also of the factorial, polynomial, and an exponential, and we do not have n to the n anywhere around here. So this is a great time to try the ratio test. So the ratio test is also a limit. Much easier to find limits than it is to find series. So you see a lot of these tests will convert things into limits. We do an plus 1 over an. And again, we're looking for something which is not equal to a specific number. Before, we're not getting equal to 0. For the ratio test, it has to be not equal to 1. So that's the break point where we're not really sure whether it goes converging or diverging, if it's equal to 1. Otherwise, we know that they both converge, diverge together. Okay. So I said that a little bit wrong, but I'll clarify it when I get to the end. So an plus 1, an. So what do we do here? If you remember doing this in the previous homework assignments, an is just literally the series. So this is n factorial over n squared 2 to the n. So that an is just literally the function, right, in our series. Right. So what is an plus 1? An plus 1 is the exact same formula, the exact same function, but I'm replacing n with n plus 1. So instead of n factorial, I have n plus 1 factorial. And instead of n squared, I have n plus 1 squared, and 2 to the n becomes 2 to the n plus 1. So I'm literally just doing all the plus 1s for n's on the top and just leaving the function as it is on the bottom. The absolute value bars just say get rid of any negatives. If there are any negatives, there are no negatives in this problem, so I don't need the absolute value bars. And now I just need to simplify this big old mess. It does simplify a lot easier than it looks like it might on first glance. So don't panic. Just remember, it will simplify if you just apply some of the basic algebra we know. So I'm going to write the top thing as it is. And I'll do the simplification of the bottom. I'll flip and multiply the bottom. All right. So now, although we don't have anything identical on the top and the bottom, we do have things that significantly simplify. So for example, we have 2 to the n plus 1. That was supposed to be in blue. 2 to the n plus 1 and 2 to the n. These are both exponentials of the same base. If you remember your algebra, if you have two, power things with the same base, you can subtract the exponents, assuming you're dividing those two. We're dividing this two, so we subtract the exponents. Or you can think about the fact that you have n plus 1 2's on the bottom and n 2's on the top. You literally just have one more 2 on the bottom. So what this happens is we get a leftover 2 on the bottom, or 2 to the negative 1 on the top if you just want to do literally subtraction. So if you had 2 to the negative 1 on the top, then it's the same thing as just 2 on the bottom. All right, similarly wise, the n factorial and the n plus 1 factorial simplify. So how do they simplify? Well, n factorial is just defined to be n times n minus 1 times n minus 2, dot, 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 all the way down to 1. What is n plus 1 factorial? Well, it's the same idea, but instead of starting at n and going down one step every single time, we start at n plus 1, and then we go down one step each time. So if I start at n plus 1 and I go down 1, then my next number is n. N plus 1 minus 1 is n. If I minus 1 again, I get n minus 1, and I'm going to all the way down to 3 times 2 times 1. So writing it out may help you see that basically everything divides everything out. The n divides the n minus 1 divides the n minus 2, the n minus 2, they all divide, the 3 divides by the 3, all of them died except for the n plus 1 on the top. So I'm left with an n plus 1 on the top. And finally, the n squared and the n plus 1 squared also simplify. I'm going to show you how they simplify just by distributing. So n squared is just n squared. And n plus 1 squared is just, n plus 1 times n plus 1. So it's n squared plus 2n plus 2, like that. Okay, so now we need to figure out this limit on the top. I'm going to have to go over here a little bit. On the top, I have n plus 1 times n, which is n cubed plus n squared. On the bottom, I have 2 times this n squared thing, so 2n squared plus 4n plus 4. And now I have a simple polynomial divided by a polynomial. A lot of you already know you can look at the highest powers on these things and, figure out that. We can also use L'Hopital's rule. If we want, we can also divide by the highest power of n, which would be n cubed. So lots of ways of doing this. This is infinity over infinity, which you can do in many, many ways. I'm not going to go through the steps because we've done lots of these before. But we're going to get something which is infinitely big on the top. Well, we'll put it this way. We get basically something like a 1 over 0, which is definitely not equal to 1, right? 1 over 0 is infinitely big. So we know that the ratio is greater than 1. Okay, so maybe I should say infinity. So this is going to tend towards positive infinity. It can't go to negative infinity. These are all positive numbers. They can't go to negative infinity. For the ratio test, if it's greater than 1, we know that the original series will diverge. So this original series, which was n factorial over n squared 2 to the n, diverges. If it's less than 1, then we know that it converges. And if it's equal to 1, we don't know anything. That's when the ratio test is sort of at that balancing point. So our limit here is greater than 1, so we know that the original series diverges by the ratio test. We should specify or justify how we're getting the answer. All right, so that was example B. We used the ratio test. All right, let's keep going on. Okay. So example C, we have n cubed plus 4 over ln n. So we have, again, if you look at your hierarchy of functions, you have something which is a polynomial n cubed on the top and a natural log on the bottom. And just to remind you, natural log is the smallest of the ones that go to infinity, and the polynomial is super larger than the logarithm. So if we were going to guess, we would guess that the n cubed is so much larger than the ln n that the ln n doesn't really matter anymore. That's the idea there. So given the fact that n cubed is so dominating, we can think of this sort of like just the series of n cubed over 1 or something. Just get rid of the ln n, and the sum of n cubed will diverge by the p-series test. So we could do some sort of comparison here, thinking that this thing is going to diverge most likely. However, as I mentioned before, it's always nice just to try the divergence test because it's so easy to do. Let's just try it. So we take the limit as n goes to infinity of the sequence here. And we get infinity over infinity. Both these functions go to infinity. I do know how to differentiate these, so I'll just use L'Hopital's rule. The derivative of the top is 3n squared. The derivative of the bottom is 1 over n. Oops, I forgot my limit. Okay. Let me write limit. I do have to write limit every time. The top is 3n squared. The bottom is 1 over n. When I differentiate the top and the bottom, I just simplify this using basic algebra. And this gives me 3n squared times n, which is 3n cubed. And the limit as n goes to infinity of 3n cubed is infinity. Now, remember, the divergence test says that if the limit is not equal to 0, then immediately know that the series diverges. So this series of n cubed plus 3 over, or n cubed plus 4 over ln n diverges. And what's my justification? The divergence test. So my divergence test, my limit was not equal to 0, so I'm done. I know this diverges. Probably easier than doing a comparison test or something else like that. Okay, we got a few more to do here. I think I have 8 or 9 total different examples of series tests to help you with your repertoire, your examples you have seen before, and will help you think about the ones that you see on homework and tests and things like that. All right, so for example D, I have 2 to the n, which is a exponential. We have 3 to the n exponential, 5 to the n exponential. These are all exponentials. What do we do here? There's no hierarchy of one over another because they're all the same type of function. They're all exponential type functions. I can perhaps simplify this algebraically. I could take the limit. I could take the limit as n goes to infinity of 2 to the n plus 3 to the n over 5 to the n. This actually does not equal 0. I mean, it does equal 0. So, I mean, this problem is it doesn't really do anything. So I just want to shortcut this to make the video shorter, but the divergence test doesn't tell us anything for this problem. So we need to go on to a different test. And what I wanted to show you on this one was just algebraic simplification. Don't forget your algebra is what I'm trying to say, right? So this guy, we can just write this as 2 to the n over 5 to the n, and then 3 to the n over 5 to the n. This is our basic algebra, where you can just, it's the distributive property, right? We have two things divided by 5 to the n, so you divide each one by 5 to the n. And then because these are series, if both of them converge, we can separate them into two separate series. Oops, that should be 5 to the n on the bottom. And I need to write this a bit clearer so people doesn't think it's 2 times n. 2 to the exponent of n over 5 to the exponent of n plus this other one, which would be 3 to the exponent of n over 5 to the exponent of n. So we can just write these as two series and see if these both converge, and then the converging plus converging is still converging. But these do both converge because they're both geometric series. If you don't see that they're both geometric series, let me remind you again of your algebra. 2 to the n over 5 to the n, they have the same exponent n. So you can write this as 2/5 to the n. And the other one would be 3/5 to the n. So we're going to say that both converge by a geometric series test. Geometric series test. This R value right here is 2/5. Remember, if it's less than 1, then it converges. This R value is 3/5, which again is less than 1. So it converges, right? So we have converges plus converges. Converges means it adds up to a number, right? So if it adds up to a number and then we add another number to it, it still adds up to a number, right? Neither of these are infinity, they're just numbers. So both converge by the alternating series test. So the original series, also converges. And if you want to, you can say a number plus a number equals a number. Right? That's the reasoning, right? Converges means adds to a number. Number plus number is number, so we know that the original series also converges. All right, onward. Example E, we have 1 plus 2 over n to the exponent of n. Inside this lovely little series thing is a variable n, and it's raised to an exponent of n. So this is a variable thing raised to a variable thing. A variable thing raised to the variable thing is the root test. It's when you have n to the n. N to the n doesn't mean like exactly n to the n. It means a variable raised to a variable type thing. So when you have a n type variable raised to an n type variable, then that's a great candidate for the root test. So we use a root test. So what does the root test say? Well, again, you're taking a limit instead of doing the actual series. And you're doing our original series here. Oops, 1 plus 2 over n to the nth. The way the root series says is you take your an, your original series function, right? That's so bad. I have to spend a moment to rewrite it just so it looks better. That's your original series function, 1 plus 2 over n to the n. And you take this and you raise it to the 1 over n power, right? That's the idea of the root test, is you take your thing and raise it to the 1 over n and see what you get. Okay, hold on 1 second. Okay, I'm back. So yeah, so the root test, we're just doing our original series to the 1 over n, doing that limit of that sequence, and we see if we get an answer not equal to 1, just like with the ratio test. So what do we get here? Well, what's nice is that the n and 1 over n will undo each other because they multiply to equal 1. So I end up with just the limit as n goes to infinity of this base 1 plus, that's a 2 over n. And now as n goes to infinity, this goes to 1 plus 2 over infinity, which is 1 plus 0, which is 1. Now, unfortunately, the root test only gives us a conclusion if it is not equal to 1. Greater than 1 would tell us that it diverges. Less than 1 tells us it converges. Equal to 1 doesn't tell us anything. So this problem is definitely a candidate for the root test, but the root test, unfortunately, doesn't really give us a definitive result. So we have to rely on a different test. So what other tests we can use? Well, we forgot to use the divergence test in the very beginning, and I mentioned that's a good place to start. So let's go back to the start and let's try the divergence test. Okay, so divergence test. So for the divergence test, what you do is you just do the limit of the sequence here, and you see if you get a non-zero answer, right? If you get 0, we don't know anything. If you get a non-zero answer, then we know that the series diverges. It's a divergence test. So we're going to do this thing. All right, so as n goes to infinity, well, we know what the 1 plus 2 over n is. We just did 1 plus 2 over n over here, and we got 1. So the inside stuff goes to 1, and then the exponent is n goes to infinity. 1 to the infinity, if you remember from your previous calculus work, is indeterminate, just like 0 over 0 and infinity over infinity, and there's 7 of them. So indeterminate means we can use L'Hopital's rule. So we can use L'Hopital's rule. Although you cannot use L'Hopital's rule until you simplify it algebraically. So let me remind you how to simplify this thing algebraically so that we can use L'Hopital's rule. All right, let me just make some more space off to the right. All right, so once again, we're taking the limit as n goes to infinity of 1 plus 2 over n to the exponent of n. That's what we're looking for. So to simplify this, there's different ways of simplifying it. Some people write this as e to the log. I tend to be a little bit more simplistic about doing it. And I just say, let's let y be the limit. So if I can get an answer for y, if I can do some algebra and find that y is equal to 7, then I know this limit's equal to 7. So why did I let y equal this? What's the purpose of y? It's to help people think about the fact that now that we have an equation, we can do the same thing to both sides of the equation. And once we do the same thing to both sides of the equation, we can simplify it depending on what we do. And what we do when we have these complicated exponentials is you take the log of both sides. So we're going to take the log of both sides. This gives us the natural log of y equals the natural log of this limit. I'm going to put the natural log inside. Limits are well defined, so you can do that like this. All right, so now what does the ln do? It allows us, if you remember before, to bring down the exponent n as a multiplier in front. So this becomes, I still have my ln y on the left side. On the right side, I have my limit, and I have n times natural log of 1 plus 2 over n. Right, so now I no longer have this complicated variable to a variable anymore. Logs are very nice in getting rid of that variable, in the exponent. So we have n times ln of 1 plus 2 over n. So this simplifies. Again, we have ln y on the left-hand side. On the right-hand side, we just put the n on the bottom. It's kind of the reverse of flip and multiply. It's like the flip and divide. So ln 1 plus 2 over n. And on the bottom, we have a 1 over n. Why did we do that? Well, because we need a 0 over 0 or infinity over infinity, use L'Hopital's rule. And so we have to make it into a fraction to be able to use L'Hopital's rule. So I just kind of put the n on the bottom as a 1 over n. That way I can use L'Hopital's rule. I forgot to write my limit here. All right, so what happens? Well, we get ln of 1 plus 2 over n. Remember, we know what 1 plus 2 over n is. We did it, right? 1 plus 2 over n goes to 1, right? So the top goes to, this is supposed to be an arrow. Top goes to ln of 1. The bottom goes to 1 over infinity. ln of 1, the natural log of 1 is 0. 1 over infinity is 0. So we can use L'Hopital's rule. So now we do L'Hopital's rule. L'Hopital. I still have ln y on my left. I haven't forgot about that. L'Hopital's rule just simplifies the limit, so I still have a limit to take. What I do is I do the derivative of the top, derivative of the bottom. The derivative of natural log of stuff is 1 over that stuff times the derivative of the inside function. The derivative of 1 is 0. The derivative of 2 over n is negative 2 over n squared, because it's like n to the negative 1, right? On the bottom, I have the derivative of 1 over n, or n to the negative 1, is a negative 1 over n squared. We're almost done, I promise. Okay. Do I have more space over here on the right? I do. Okay. So I have my negatives divide out. Let me use a red, I guess, still. Oops. Messed up my UI. Okay, there we go. The negatives cancel out here or divide out. The n squareds divide out. And we're left with 2 on the top and this crazy thing on the bottom. So I get my ln y is equal to the limit. Over here, I have 1 over 1 plus 2 over n, and then I have a 2. Right? I guess I can write the 2 on the top with the 1, because 1 times 2 is 2. I'll just put those together so it looks a little nicer. So that's my limit. Right? So what does this become? This becomes 2 on the top and 1 plus 2 over 0. 1 plus 2 over 0. Is that true? That looks like it's true. So what does this become? This becomes ln of y equals the limit as n goes to infinity. It becomes 2 over 1 plus 0, which is 2. Now, that's not really the answer to our original problem, because remember, we said originally that y was the limit, and we have found ln of y, not y. So to find the limit, we just raise both sides with a base of e, and that means y, which is our limit, right? Our answer is equal to e squared. So let's recap here. We tried the root test and we didn't get anywhere because the root ended up being 1, which is the number that we don't really know whether it's going to converge or diverge. We tried the divergence test, which means you just take the limit to see if you get a non-zero result. If you get non-zero, we immediately know that the series diverges. We got an indeterminate form of 1 to the infinity, which we had used algebra to simplify. My algebraic technique that I show students is to let it equal to y. So y was equal to the limit. We simplified it using a bunch of algebra, including take the natural log of both sides, and we got y is equal to e squared. So the limit was equal to e squared, and the limit is not equal to 0. E squared is like 2.7 times 2.7, which is 8 point something, whatever. I know it's not equal to 0. So therefore, when you take the limit of the sequence and it doesn't equal 0, we know that the original series diverges. So this thing right here, oops, let me keep going over here. So I'll do it in blue. I guess I'll do it in red. So our original series here, 1 plus 2 over n to the power of n, diverges by the divergence test. Okay, nice, interesting question there. I would have tried the root test first because it looks like the limit The divergence test is complicated, right? Because you have to do all that simplification. So personally, if I was doing this problem and didn't know the answer ahead of time, I would try the root test just because it's obviously variable to a variable, but I would be disappointed because the answer was one, and I have to go back to use the divergence test, which does indeed show that it diverges. All right, so I guess I bring that up. I made this problem up just to kind of give an example of the root test, but also I guess to demonstrate that you're not always gonna like choose the right thing. Sometimes you're gonna get one or whatever, and it doesn't tell you anything, and that's just the nature of these types of problems. You're not gonna get 100% hit rate on knowing which is the easiest series test to use on any given problem. All right, we got a few more to do here, and then that'll be it for you're just doing lots of examples. Feel free to pause this if you want to try the examples, but I'm just doing lots of examples today of choosing which series convergence divergence test to use on any particular given series function. All right, so I have this one here has a cosine in it, n to the exponent of cosine pi divided by pi. Yikes. The yikes, I guess, is maybe the wrong word, but for many students, if you don't remember a lot of your trigonometric ideas or formulas or values or things like that, this can seem a little intimidating because like what the heck do I do with cosine? Cosine is a function where you put in an angle and it gives you out a value, right? It gives you the x value on the unit circle. Or if you want to think simplistically in terms of a first quadrant triangle, it gives you adjacent over hypotenuse. That is a very dangerous definition to work with in calculus because you don't always have a first quadrant triangle. So it's best to think of this as the x value on a unit circle for a given angle. If the angle is pi, then we've traveled halfway across the circle, and the x value over there is -1. Also, you can just put it into your calculator. But if you're sort of familiar with the trigonometry, you look at cosine pi and say, oh, that's just -1. Why didn't they write -1 there? They're being tricky. Okay, that was me being tricky. So this is really n. Cosine pi is -1, and this is pi. So this is really, once I simplify it, n to the -1 over pi. So that's my series. If you want, you can write this instead as 1 over n to the positive 1 over pi because negative exponents are just reciprocals. Okay, so this is a variable raised to a number, right? N raised to the -1 over pi, or 1 over n raised to the positive 1 over pi. That is a polynomial type function called a p-series function. If you have a p-series, the p-series test is fantastic to use to evaluate these things. P-series test. So the p-series test, you look at the p-value, right? This is 1 over n to the p. So our p-value is 1 over pi. The way they write the p-series test is they always put the n thing in the bottom. So this thing right here, if it's 1 or less, it diverges. 1 over pi is like 1 over 2.7, like 1 over 3 or something. This is less than 1, right? And so by the p-series test, if you have the p-value being, I guess, less than or equal to 1, right? 1 also diverges, and anything less than 1 also diverges. We know that the original series, so the original series n to the cosine n or cosine pi over pi will diverge. Diverges by t-test. Okay, so I kind of made this a little sneaky, so it didn't look like a polynomial at first, but it is. It's a p-series test. And the p-value, if it was greater than 1, we know it converges. If it's less than or equal to 1, we know it diverges. This was 1 over pi, so it diverges. All right, so last page of examples, it looks like. Okay, and I have a few examples left over here. Okay, so ln n over n. All right, so let's not forget to use our divergence test. real quick. We'll take the limit as n goes to infinity. This looks like an easy one to differentiate. Ln n over n, they both go to infinity. So I L'Hopital. I get my limit. The derivative of the top is 1 over n. The derivative of the bottom is 1. So this becomes 1 over infinity. This becomes 1 over infinity over 1, which is 0 over 1, which is equal to 0. And unfortunately, when you get 0, you didn't really learn anything. So our divergence test didn't really result in anything, but it's always good to try, right? It just didn't take very long to figure that out. All right, so we do have this ln n thing, and we have this n thing. Let's go back to the hierarchy of functions, right? Ln n is way, way smaller than n. So ln n is the logarithmic, n is a polynomial, it's n to the first power. And just to, I guess, recall for those people who are looking at this, ln n is the smallest thing that goes to infinity. X to any power, as long as the power is greater than 0, is substantially bigger than ln n. Even x to the 1 is way, way bigger than ln n or ln x. So looking at this thing right here, n is really the thing that dominates. Ln n is just so small compared to that. Ln n, if we just get rid of it, is like 1 or something. So it's like 1 over n. And 1 over n is our harmonic series. It's also a p series. So we're going to think this thing diverges. So if you're thinking it's diverging, you could use like a limit comparison test, or you could use a direct comparison test. We can also use another test as long as we can do it. We can't use the geometric series test because we'd have to get rid of, well, it has to be a geometric series. There's no geometric series. And we'd have to get rid of the ln n before we can use the p-series test. I'm going to demonstrate using the integral test just because it works kind of nicely for this one here. So you could actually use those comparison tests like we did in example A, but I'm going to be using the integral test. So just because I wanted to have one where I showed you the integral test. And why is this a good one to use for the integral test? Because I've integrated ln n before, right? I know I can do the integral of ln n over n. It's a very simple substitution problem. If you don't recognize it as something you can anti-differentiate, then don't try the integral test. The integral test should be stuff that you can recognize. Oh yeah, I can integrate that thing. You would just use a comparison test instead. So we just make a u substitution. U is equal to ln n. We find the derivative. We solve for solve for dn. So I put the dn over there, it becomes n du. And so that is going to go in for there. And that is going to go in for there. And so what do we end up with? We end up with the integral ln n becomes u. I got n on the bottom. dn becomes n du. My n's divide out. And I'm left with the integral of just u du, which that one's just a p power series thing. So that's, whoops. The antiderivative of u is just u squared over 2. Right? We do have to take the limit of this thing to see what happens, but you can probably notice this thing is going to diverge. So what we're doing here is we're taking the integral from some number to infinity. So we do a limit as b goes to infinity. We can do any number to b. And then we're going to do the same thing over here. Limit as b goes to infinity. It doesn't really matter. The bottom limit doesn't really matter. But you do have to do the actual integral, the improper integral. So I'll throw in all these limit things here. Once you take the antiderivative, then you evaluate it from those two endpoints, and you're still taking the limit, of course. When you plug this in, you get b squared over 2. So we still have our limit thing. If you plug in b, you get b squared over 2. And you plug in a 2. You get 4 over 2. So that's my antiderivative. And then I find out what happens when the limit of b tends to infinity. And so this becomes infinity squared divided by 2 minus 2. And infinity squared divided by 2 is still infinity. Infinity minus 2 is still infinity. So this tends to infinity. So the integral diverges. What the integral test says, is if you do the integral instead of the series, whatever happens with the integral, converging or diverging, is the same thing that happens to the series, converging or diverging. So we say that since the integral diverges, then also the series, the series diverges. And that's by the integral test. Integral test. So there's an example of using the integral test. If you can recognize, it can be antidifferentiated. All right, couple more examples for this video with lots and lots of examples. Okay, 3 more examples. 3 more examples, and then I'm done. All right, so h cosine n pi over times ln n over n. So we're going to be looking at this wonderful Lyell series. So we know cosine pi is -1 from our previous problem, but this is cosine n pi. N is the thing that's moving, right? N equals 1, n equals 2, n equals 3. N is the parameter that moves in these things. Let's write out a few of these just so that people can see what's going on here. N equals 1, n equals 2, n equals 3, that kind of thing. If n equals 1, we get our cosine pi, which is -1. We get ln of 1, which is 0 over 1. So that's all 0. Doesn't do much. If n equals 2, I have cosine 2 pi. What is cosine 2 pi? Well, 1 pi would be -1, and 2 pi would be +1. You may remember seeing this in a previous video, but cosine n pi is one of those things that switches between +1 and -1. So this is going to be 1, and then it's going to be ln of 2, and then over 2. N equals 3, we have 1 pi, 2 pi, 3 pi. We're back to the -1 thing. So we have -1 ln of 3 over 3. This, my friends, is an alternating series, right? It switches between positives and negatives, right? The next one's going to be +1 again. It's going to be ln 4 over 4, right? It switches between positive and negative, like that. So we know it's an alternating series. Alternating series, we can use the alternating series test. Alternating series test. All right, so what does the alternating series test say? Well, first of all, you get rid of all the negatives, right? So then we examine the series, the example of the sequence, examine the series here without the negative part. The negative positive part is the cosine pi n. So we just examine this part right here. Right, so get rid of all the negatives. You have to say that it alternates. It does. We need to know that the terms decrease. And the answer is yes, because we know that n is infinitely larger than ln n. So this thing dominates. This thing right here, I also told you in a previous video, we always know that n is larger than ln n as long as n is at least as big as 2. So we're going to be able to know that terms decrease. Yes. And we could say because n is way bigger than ln n. All right. The other thing we need to know is we need to know that the limit goes to 0. Question mark, right? I don't know that it goes to 0, but if we can show that it goes to 0, if we can show that the terms decrease, and it alternates, then we know it converges by the alternating series test. Alternating series test, we examine, this word is supposed to be examine. Can't read my own handwriting sometimes. Okay, most of the times. Examine. So we're examining this, this is an E, examining this series without the negatives. We need to find out the limit to see if it goes to 0. I think we did do that limit before, but let's just do it again. Okay, so we take the limit as n goes to infinity of ln n over n. This is infinity over infinity, so we can use L'Hopital's rule. So we still have a limit. L'Hopital's rule just simplifies the limit. The top becomes 1 over n, bottom becomes 1. This becomes 1 over infinity over 1, which is 0 over 1, which is 0. Right, so we definitely know that the limit's equal to 0. So that's supposed to be the green check mark that we like. The limit goes to 0. The terms decrease. It alternates. That's what you got to do for the alternating series test. So this original series, the cosine n pi ln n over n, converges by the alternating series test. All right, so use the alternating series test when the series alternates, right? Positive, negative, then you're going to use the alternating series test. All right. 2 more. Example I. Well, example I has this -1 to the n thing. -1 to the n is the classic, alternating between +1 and -1. So we think, okay, well, that's, probably going to be an alternating series test. Let's write out some terms to make sure that it actually alternates. My advice I've given many times before. So let's write this out. So we have n equals 1, n equals 2, n equals 3, etc. So for n equals 1, -1 to the 1 is -1. 4 plus -1. I'll write it out. 4 plus -1 over 1 squared. 4 plus -1 is 3, and 1 squared is 1, so it's 3 over 1. For n equals 2, we get 4 plus -2 squared over 2 squared. Putting in n equals 2, a -1 squared is +1. 4 plus +1 is 5. And the bottom 2 squared is 4. So we have 3 over 1, 5 over 4. Let's just do one more. We get 4 plus -1 cubed over 3 squared. Or, yeah, 3 squared. -1 cubed is -1. 4 plus -1 is 3. And the bottom becomes 9. So even though it has a -1 to the n in there, it is not alternating between +1 and -1. It does not alternate. So you cannot use the alternating series test for this problem. So what do we do? Well, there's a couple things. You could, if you remember before, just simplify this using the distributive property, making it 4 over n squared plus -1 to the n over n squared, and then test both of those series separately. That would be a good strategy. That would work quite well for this problem. I'm also just going to say, let's see an example of the direct comparison test. So we could use the limit comparison test or the direct comparison test. The limit comparison test doesn't work here because when I do the limit, I get 1, and the limit comparison test says you can't get 1. So if I threw away all the stuff on the top and I just did my limit comparison with my simplified version being just like, 1 over n, or let's just say 4 plus or 4 over n squared. Let's get rid of the -1 to the n part, just making it much easier and making it 4 over n squared. You could also do 1 over n squared. Doesn't really matter, but just kind of get rid of stuff to make it simpler. You can take the limit as n goes to infinity of our an divided by our bn. which ends up being, well, I'll write it out. It's 4 plus -1 to the n over n squared divided by bn, which is 4 over n squared. This ends up being equal to 1. So according to the limit comparison test, it has to be not equal to 1 for us to get a result. I'm not going to go through all the details. The details of how to find this limit is basically using the squeeze rule, or you can just squeeze it between two numbers like 3 and 5. It doesn't really go anywhere, but this is an example I want to show you for using the direct comparison test. All right, so for the direct comparison test, what we do is, okay, so for direct comparison. So for the direct comparison, I'm going to rewrite this series right here. Our original series, our original sequence that we're taking a series of is 4 plus -1 to the n over n squared. To do the direct comparison test, you first have to have an idea of whether you think this converges or diverges, because it changes what our bn is depending on whether we think it converges or diverges. So do we think this converges or do we think this diverges? Well, the top is just numbers. The top was a 4, either +1 or 4 -1. So the top is a constant. The bottom is n squared. N squared is definitely going to infinity, and the exponent is bigger than 1. So as a p-series, this is going to converge. So we should think converging because you have a p-value that's greater than 1. Right? It's a p-series type thing with p greater than 1. So why does it matter that we think that it's converging? So for the converging version of the direct comparison test, right, what you do is you find something which is smaller. I always have to draw a picture. So our an, okay, here, I get it. So I always draw a picture just to help you out here with where I'm going with this, is that we have our weird an function. We don't really know what it does, right? If we want to show it converges, that means the amount of stuff, the amount of area or whatever, has to be small. So if we find a bn, which is larger, but also converges, right? So the bn has an area here, has an amount of stuff, which is finite. Since the an is lower, it also has to be finite, right? So we're looking for a bn which is larger. So we need to find a bn that's greater than an. If we find something which is larger that still converges, then the smaller thing also must converge. All right, so how do we find a bn that's larger than an? Again, we just kind of make things very simple just so that we'll be able to do a simple comparison. So we have 4 plus either -1 or 4 plus +1. I guarantee you that 5 will always be either bigger or equal to bigger or equal to 4 plus -1 to the n over n squared. If you want, you can make this 15, that's also bigger. It doesn't really matter. You need to find something which is bigger than the an, right? And so I think the math people who write your book would use 5 there. So I'll use 5 as well. But as long as you can guarantee that it's bigger, then you can use the comparison test. So now we need to look at this bn thing. So the series of bn converges by p-series test. And that p-value is equal to 2, which is greater than 1. Right? If you have a p-value greater than 1, you know that it converges. So our simplified version converges. So therefore, our original series converges by the direct comparison test. All right, that was my attempt to show you an example of the direct comparison test. and why you might choose that for this problem. If we try the limit comparison test, it doesn't really give us an answer that gives us a definitive knowledge of whether whether it converges or diverges. But the direct comparison test, just by knowing that it converged ahead of time, or at least guessing that it converged ahead of time, we could make a very simplified version of your BN, which we know for sure converges. And since BN was larger than AN, the larger thing converges means that the smaller thing also has to converge. That's what the direct comparison test is doing for us. Okay, we are almost done. We're almost done. All right. Or maybe we are done. No, I don't think we're done. I think a little more. There we go. We have a J right here. Now the J is actually a pretty fast problem. Here we have 1/2. I included this problem just as a finisher because I've had a lot of students who just kind of get confused when it's simple. Like they're used to really complicated things, and like if it's simple, like, oh, 1/2, well, that's a number that converges, right? So that's kind of a common error that students make. So I just want to kind of bring up this last one. If I want to write out the terms, which I like doing, right? N equals 1, n equals 2, n equals 3, right? The first term is 1/2 because there's no n's in there. The second one is 1/2. Next one is 1/2. So all the terms in the sequence are 1/2 plus 1/2, or 1/2, 1/2, 1/2, and a series adds them together. So the series of 1/2, that's equal to 1/2 plus 1/2 plus 1/2. Remember, series adds up all the terms together. If I add 1/2 an infinite number of times, I will get infinity. I know half is a number smaller than 1, but 1/2 plus 1/2 is 1. And then if you add another half and you get bigger than 1, 1.5, then you get 2, then you get 2.5, then you get 3 and 3.5, and you're going to get to infinity. It's going to get there. So this is diverging. You can do diverging just because it adds to infinity, and that in fact is what the divergence test is. If you take the limit as n goes to infinity of our sequence, which is 1/2, there are no n's in here, right? It's not like 1/2 to the n. It's not like 1/2 times n. It's just 1/2. So the limit here is equal to 1/2, which, as we know, 1/2 is not equal to 0. So it diverges by the divergence test. Okay, so there were a whole bunch of examples of trying to think about which divergence convergence test to use for any particular series function that you're being asked to evaluate. I tried to give examples of each of the 8 kinds of series tests that we learned in this class. And, options, some problems, definitely you can use more than one different type of convergence test. And some of them you could use more than one, but some are much easier than others. So I tried to give some examples of all of that stuff. Hopefully you found this useful, and you will reach out if you do have any questions or any other series that you would like to help evaluate on whether they converge and diverge, and what test would be the sort of smart, easy choice to help facilitate that conclusion. All right, well, please enjoy your day, and hopefully I'll see you in Zoom or perhaps just on the next video.